Hello students, in this video we are going to discuss how to design synchronous mod 5 counter. Okay, so mod 5 counter. So we have to follow some of the steps in order to design mod 5 counter. In your CA2 exam, they will ask mod 10 counter. Okay, so design of synchronous mod 10 counter. So in this video we will discuss mod 5 counter. I will tell you what to do for mod 10 counter. Okay, as we know that the step 1 is we need to determine the number of flip-flops based on this equation, right? 2n greater than equal to n. Here the lowercase letter n represent number of flip-flops, which means number of bits required to represent mod 5. I mean 5, right? So for example, if I use n is equal to 2 means we can able to represent capital N is equal to 4, right? So how we got this 4? 2 to the power of 2 is equal to 4, but I want to design mod 5, so I have to increase this lowercase letter n, right? 2 to 3. So if I put n is equal to 3 means I will get capital N is equal to 8. So I can able to count up to mod 5, right? So mod 5 means we can able to count from 0 to 4. So whenever it reaches 5, so the result is zeros. We will discuss that one. Okay, so here we are going to use JK flip-flop. Okay, so we have, in order to design this logic circuit, so first we have to find out the characteristic table by using this excitation table of JK flip-flop, right? um, so actually we are going to find out the excitation table of uh, mod 5 counter, okay, by using the excitation table of JK flip-flop. Okay, so by using this table we have to find out the characteristic equation using K-map. By using that characteristic equation we need to design the logic circuit. Okay, we will see one by one. So this is your excitation table for mod 5 counter. Excitation table for mod 5 counter. Here the number of bits is equal to 3. So here, as it is a number of flip-flop, number of flip-flops are 5. So we have totally 6 inputs, right? For each flip-flop we have JA, KA, JB, KB, JC, KC. So 6 inputs and 6 outputs. So that's why here we have written um, QA, QB, QC. This is your present state. QC plus 1, QB plus 1, QA plus 1. This is your next state. So this is your LSB, MSB. Similarly, this is your LSB. This is your MSB. So just you refer this excitation table of JK flip-flop. You know very well. We have discussed it while discussing the JK flip-flop. Your present state is 0 and next state is also 0. So you have to find out what is my input, right? So first condition is whenever your inputs are 0 0 and your present state and next state is also 0, it doesn't change anything. So 0 1 means it is a reset state. So my present state is 0, my next state is also 0. It is a reset state, right? So that's why here we have written this is my 0 0, right? This is my J, this is my K, right? In this condition my output doesn't change, so that's why it retains present state and next state also zeros. And one more condition is 0 1. This is my reset state. So that's why this one we have written as 0, and we can able to write 0 1 as don't care, right? So that is my input condition. So next 0 1. So 0 1 means my present state is 0, my next state became set, right? So toggle, it became toggle. My present state to next state, it became toggle. So the input conditions of 1 1 jk, right? This is my j, this is my k. Another one is it set. So that's why I can write 1 and this one is 0. So that's why I can able to write 1 don't care. So that is my input condition. So similarly we have to find out for other two conditions. So we will come to for this excitation table for mod 5 counter. So this is my present state, this is my next state for each flip-flop. Okay, so this is my 0. My present state output is 0, my next state output is 1. This is my 1. Similarly, my present state output is 1, my next state output is 2. My present state is output, my present state output is 2, my next state output is 3. My present state output is 3, my next state output is 4. My present state output is 4, my next state output is 0, because it counts from 0 to 4. Almost it is a mod 5 counter. Whenever it reaches to the 5, it became, my next state become 0, right? Similarly, for mod 10 counter, you have to write from 0 to 9. So you have to write for binary number 0 to 9. So whenever it reaches my 9, my next state becomes 0 for mod 10 counter. This is mod 5. So whenever it reaches to 4, my next state became 0. Similarly, whenever for mod 10, whenever it reaches to 9, my next state became 0. Okay. So after that here, as it is a 3 bit we have used 3 flip flop, it counts from 0 to 7. So but I need, it is a mod 5 counter. So up to this one we need. After that mod 5 means my next state, it is a don't care, I don't know. Sorry, binary number 5, and binary number 6, my next state, I don't know, it is a undetermined condition. And also 7 also, it is a undetermined condition. By using this present state and next states, I am going to find out what is my inputs. Okay, so for example, see here, just consider only QC present state, and in the next state QC plus 1. See here, this is my 0, and this is my next place is also 0. See here, 0 0 means 0 don't care. You have to write 0 don't care. Next one is again, it is a 0 0 0 don't care. 0 1, now it became 0 0, it is also 0 don't care. Up to here it is 0 don't care. After that, here it is my 0, my next state is 1. So you have to see this excitation table of JK flip flop. So 0 1 means 1 don't care, you have to write 1 don't care. Similarly, this is my 1 and my next state is 0. 1 0 means don't care 1, you have to write don't care 1. For the remaining 5 6 7, it is an undetermined condition, you have to write as like that. For all the input condition of JC, KC, JB, KB, JA, KA, these are undetermined. So whatever we have written here, it retains here itself also. Okay. So similarly for QB plus 1, QA plus 1, you have to find out the inputs by using this excitation table. Once if you are frame the excitation table of mod 5 counter, right? Now you have to find out the characteristic equation. So you have to find out the characteristic equation for JC, KC, JB, KB, JA, KA, right? See here, I will teach you only for JC. For the remaining, you have to find out. So JC, so I have to find out the characteristic equation for JC. This is for JC. Okay, so this is a 3 input variable. So this is your 3 input variable. So I have to use 3 input variable K map. You have to take from QC to QA. QC, QB, QA. So this one is your QC, QB and QA. Right? 000, 001 and 110. You know how to plot the schema. I am not going to teach this. So once if you are plotting the schema, you have to put the decimal value of each cell. This is 0 1 3 2. For example, if I take this one, how I have written this 3? 0 double 1. 0 double 1 means what? It is 3. 0 1 0 means what? It is 2. Right? First you have to plot the K map. After that, see here only this column, see only this column. This is my 0 1 2 3. So wherever I have 3, I have to put 1. Where is our 3? Here. So I have wrote 1. For the remaining 4 5 6 7 4 5 6 7, I have wrote don't care, because we are getting don't care at the input conditions of JA, right? So not JA, JC, right? So after finding this one, you have to find out the characteristic equation by performing grouping. So here I am getting a pair group. So one don't care. So my output is, so after grouping, right, you have to find out the characteristic equation. So you know that. So for the JC, here we are grouping these two cells, so QB, QA. Similarly for KC, so based on these values, right? So KC, based on these values, you have to fill this table, right? And so it is a octa group, right? So this is octa group, so we will get KC is equal to 1. This is octa group, okay? So this is for JB. This is for JB. This is a quad group. So these two are different, right? So here the common is this one and this, right? So that's why we are taking QA. So similarly, you have to find out for KB, JA, KA. After find out in the characteristic equation, this is the time to draw the logic circuit or logic diagram, right? So as we are using the JK flip-flop and JK excitation table, we have to use 3 JK flip-flops. Here we are using the clock, right? It is a bubble, indicates it triggers at the negative edge trigger, right? You know this. This is your positive edge triggering. This is your negative edge triggering. As we are using the bubble here, we have to perform the negative edge triggering of flip-flop in the, as it is a synchronous mod 5 counter, right? So here we are using the clock pulse. For all the flip-flop, we are using the external clock pulse. You have to observe this. See here, we are using for every flip-flop the main clock pulse. But in our asynchronous, what we did, we the output, the first flip-flop we have used the external clock pulse, right? So but for the second flip-flop we have used the output of first flip-flop. For the third flip-flop we have used the output of second flip-flop. But in the synchronous we have used the, for all the flip-flops we have used external clock pulse. So that is the main difference between the synchronous and asynchronous counter. And here the connection is somewhat different when compared to the asynchronous counter. So see here, for the JC we have to connect QB, QA. This is our JC. We have to connect, um, this is my AND gate, QB, QA, the output of QB and output of QA, right? After that, for KC, for KC is 1. See here, the KC here we have connected to high. So 1 means high, right? After that, for JB, QA and KB QA. So you have to connect it output of QA, right? This is my QA. So we have to connect JB, and also the same output we have to connect it to QA, right? So after that, JA and KA. JA is QC bar. For JA input, we have connected QC bar, right? See here, we have taken QC bar output. So for KA, we have to connect high. It is equal to 1, right? So we have connected everything. So after that, this is my JB is QA is my output, QA, QB, QC. This is my LSB, this is my MSB, right? QA, see here, this is my LSB, this is my MSB, QA, QB, QC, right? So then after we have to draw the timing diagram, right? So as it is working under the negative edge of clock pulse, right, every output triggers at only negative edge of clock pulse. Each flip-flop trigger at only negative edge of clock pulse. Initially, all the outputs are 0, QA, QB, QC. After that, once if we are triggering the all flip-flops at negative edge, so my first flip-flop output is 1. My next flip-flop output is 0, right? It triggers. If I have 1 means it, if I have QA is 1 means my QB is triggered. Until then my QB output is 0, right? So the first flip-flop triggers for the every clock pulse, right? First, second, third, fourth, fifth, sixth, like that. My second flip-flop triggers every 2 clock cycle, 2T. It triggers 2T. It triggers for every clock cycle. This one is triggered for every 44 clock cycle, right? So we have discussed in detail in our class, right? So after that, whenever we are getting 1 in the first flip-flop, the second flip-flop triggers. So whenever we are getting the 1 in the second flip-flop, the third flip-flop triggers. Until then it retains the same state up to 4th clock cycle. So once it reaches 4, right? So my for the next clock pulse, all the flip-flops should reset. It becomes, though all the flip-flops become zeros. So similarly for the mod 10 counter, so up to 9 we will get the results. From 0 to 9 we will get the result. After that 9, all the flip-flops are zeros. All the flip-flops cleared. So this is your um, mod 5 counter. In your exam they will ask mod 10 counter, design synchronous mod 10 counter. So you have to write up to 9, right? 0 to 9. So here one more output you are getting, okay, that one is QD, right? So and you have to write the timing diagram up to 9. After that 9, so it becomes 0, right? And here, so you have to use one more flip-flop. So for that one, in order to find out JDQD, so here your excitation table changes. Here you will get here QD and QD plus 1, right? Here JDKD input conditions. So it varies 0 to 9. So based on that your JD and KD input conditions also varies. I hope you are able to understand. Thank you.